All right, so I think this is recording. Let's take a look at this skill 11A. Um, all right, so if I take a look at this equation, it has infinitely many solutions. The sine of x, the sine of some angle x is equal to negative radical 2 over 2. On the unit circle, I'm going to look for a y-coordinate that is negative radical 2 over 2. Negative y values are down here in quadrants 3 and 4. And if I find this point has a y-coordinate of negative radical 2 over 2, and this point has a y-coordinate of negative radical 2 over 2. So the solutions to this equation, all infinitely many of them, are too many to list, but I can write that as 5 pi over 4 plus my coterminal angles. If I do a complete revolution in either direction, I'll end up back at that point, and the sine of that angle will equal negative radical 2 over 2. If I'm at 7 pi over 4, again, I can describe infinitely many solutions. Now, they did not want infinitely many solutions. They asked me to find the solutions so that x was between negative pi over 2 and positive pi over 2. So if I write my negative pi over 2 and positive pi over 2 in terms of a denominator of 4 so that I can easily compare them, let's do that for you. Let's think of this as negative 2 pi divided by 4 is less than or equal to x, which is less than or equal to 2 pi divided by 4, because 2 divided by 4 reduces to 1/2. All right, so the 5 pi over 4 is too big. It's bigger than pi over 2. So I'm not going to use it. And the negative pi over 2 to positive pi over 2, I know that's the right half of my unit circle. So there's the justification for getting rid of this point, not even having it in consideration. But 7 pi over 4, if I let n equal 0, I've got a problem that 7 pi over 4 is bigger than pi over 2. So I don't want to let n equal 0 to find the solution. If I let n equal negative 1, if I replace n with the integer negative 1, then what I have is negative pi over 4. So that means that if I go in a clockwise direction at an angle of pi over 4, clockwise is negative, then I'll be at that terminal point. This is the solution that they're wanting. I found infinitely many of them, and then from that infinitely many, I reduced it to the one that they wanted that was in this interval. And that's how I'm going to approach these problems. All right, so let's look at the next one. The cosine of x is equal to negative radical 2 over 2. This equation has infinitely many solutions. I can't list them all, but I can write an equation that describes them. I'm going to start out looking on my unit circle between 0 and 2 pi and look for x coordinates that are negative radical 2 over 2. Negative x coordinates are going to be over here in quadrants 2 or 3. A negative radical 2 over 2 will occur at this point and occur at this point. So if I were writing infinitely many solutions, all possible solutions, I would start with 3 pi over 4, and I would add multiples of 2 pi. But I'm going to write 2 pi as 4 pi over 2. That would not help me at all. I want a common denominator, so let's try that again and write this as 8 pi divided by 4. 8 divided by 4 is 2, so this is just rewriting 2 pi, so I have a common denominator. It makes it easy for me to add and subtract these fractions. So 3 pi over 4, and any angle that's coterminal to 3 pi over 4, if you take the cosine of that angle, I claim it will equal negative radical 2 over 2. I also claim that down here at this point, at 5 pi over 4, the same thing, that I can add or subtract complete revolutions and arrive at that same point, but at a different angle. Now, they did not want infinitely many solutions. They did not want all of these. What they wanted in this case was all the solutions that were between 0 and pi. So in other words, they wanted the solutions that were on the upper half of this unit circle. So I'm going to eliminate this point out of consideration. Its solutions to the equation is just not the kind of solution they're looking for that's between 0 and pi. So if I let n equal 0, if I replace n with 0, I get the solution that they want, 3 pi over 4. Because remember, for comparison purposes, we can rewrite 0 as 0 pi divided by 4. That's just 0. And I can rewrite pi as 4 pi divided by 4. So really what I'm comparing is this coefficient in front of pi, this 3, and 3 is bigger than 0 and smaller than 4. Because now that I have the same denominator, I can just compare the numerators. This is the only solution in this interval for this equation. So again, I like to start out thinking, hey, I'm going to write the general solution. I'm going to describe the infinitely many solutions to this equation. And then I'm going to look and see if that's an acceptable answer or if they want me to restrict these infinitely many to just look at values of x that are between some value, if they have constraints for this problem. All right, so with the sign, I'm looking at the y-coordinate. I want to find a y-coordinate that's -1/2. Negative y-coordinates live below the x-axis, so I'm going to have one, the point of interest is here at 7 pi over 6, and over here at 11 pi over 6. All right, so I'm going to write my equation on 0 to 2 pi is 7 pi over 6. But if I generalize that and think about that over the entire domain, over the set of all real numbers, I'll rewrite 2 pi with a denominator of 6. 12 divided by 6 is 2. And this is a way that I can't list infinitely many numbers, but I can describe them in this equation. This is all infinitely many of these numbers will be solutions to this equation. And there's even more. At 11 pi over 6, the same idea. Whether you add in a positive sense complete revolutions or you go the other direction, you subtract complete revolutions, you'll end up for coterminal angles at that point in that same quadrant, and it will have that same sign ratio. So here's the infinitely many solutions for this equation, but they did not want infinitely many. They wanted me to find the solutions that were between -90 and +90, so they wanted me to work in degrees, so we'll change this to degrees. From -90 to +90 is the right half of this unit circle. So this 7 pi over 6, I'm going to eliminate it altogether. It's not even a point that's on this interval. So I want this point and any coterminal angles to that point. Now, I prefer working in radians, but since they've given this to me in degrees, I notice that 11 pi over 6 is 330 degrees, and 330 degrees is much bigger than 90. So instead of let's write this 330 degrees plus a complete revolution in degrees is 360. So I'm not going to let n equal 0. I'm going to let n equal -1. If I replace n with -1, then what will I have? Well, let's look and see. Positive 330 plus a negative 360 is -30 degrees. And -30 is between -90 and +90 degrees. So if I just go in this clockwise direction to here, then I find that a solution to this equation, which I knew there's infinitely many. So hopefully out of infinitely many, I can find the one they're asking me for. And the one they were asking me for was between -90 and +90. So this is the one they're asking me for. All right. Let's look at this. Now, the tangent's a little more difficult because in the previous ones, if I had sine, I was focused on the y coordinate. If I had cosine, I was focused on the x coordinate. Well, with the tangent, tangent is sine over cosine, or y divided by x. So I'm going to make a little bit of chicken scratches over here in this first quadrant. If I take the y coordinate divided by the x coordinate, what would that reduce to? 1/2 divided by radical 3 over 2. Well, that would be 1 over radical 3, and that rationalizes to radical 3 over 3. Okay, and this point here, y divided by x is just 1. And this point right here, if you take the square root of 3 over 2 and divide it by 1/2, the 2's cancel and you just have the square root of 3. So I can use this ratio, and over here in quadrant 2 make them negative, in quadrant 3 make them positive, and over in quadrant 4 make them negative, because remember, if tangent is y divided by x, tangent is positive when x and y have the same sign SIGN. Here x and y are both positive, their ratio is positive. Here x and y are both negative, their ratio is positive. So if I'm trying to describe the infinitely many solutions to this equation, I'm interested in not this point because it has a positive ratio, but if I go over here, this point, because it's going to have a negative ratio of negative square root of 3 divided by 3. And down here, the same thing, it's going to have a negative ratio like that. So if I want to describe this infinitely many points, I'm going to start with this 5 pi over 6. And the period for tangent and cotangent is different than all the other trig functions. It's only pi. So I'm going to add integer multiples of pi. I'm not going to be adding 2 pi or 360. I'm going to be adding 180 degrees or pi. You know, like see here, 8 divided by, this was 2 pi. Well, that's 360 degrees. That's the period for cosine, but the period for tangent is just pi or 180 degrees. So I'm going to add integer multiples of pi, which when I add pi, that comes around and hits that point. So all I have is one equation that describes going back and forth for angles that has infinitely many solutions to this equation. They didn't want infinitely many, so let's look and see what they wanted. Well, okay, they want me to work in degrees, so that's easy to change here. I'm going to erase this step just to give me more room to work with. All right. Oop, I lost the top of that 5. All right. So if I rewrite this in terms of degrees, 5 pi over 6 is 150 degrees. Pi radians is 180 degrees, 180 times this integer n. Well, if I'm looking for angles that are between negative 90 and positive 90, I'm looking at the right half of this unit circle. So if I let n equal 0, I've got a problem because 150 is not between negative 90 and positive 90. But if I replace this n with negative 1, then 150 plus a negative 180 is a negative 30. In other words, if you just rotate clockwise 30 degrees, you'll be at this point. And that's all they wanted was a solution. There could have been more than one solutions, I guess, in this right half. But in this case, the points of interest were on opposite sides of the y-axis. So there was only one point of interest in this range, and we found the angle measured to be negative 30. Negative 30 degrees. All right, so let's look at this next one. Cosine of 0. I'm looking here on the unit circle where I have an x-coordinate of 0. It happens right here at pi over 2, and it happens down here at 3 pi over 2. So this equation has infinitely many solutions. One of these solutions is pi over 2. And if I add complete revolutions to find coterminal angles to pi over 2, those will be solutions as well. So if I rewrite 2 pi as 4 pi divided by 2 is 2, so this is 2 pi. If I add or subtract complete revolutions or multiples of complete revolutions all end up at coterminal angles. And they'll have a cosine of 0, that angle will. Well, also down here at 3 pi over 2, the same thing. And if I add integer multiples, because this period is 2 pi, I'm adding 2 pi to get to that next value. Now, they didn't want me to find infinitely many. They wanted me to find solutions that were just between 0 and pi. 0 and pi is the upper half of this unit circle. Okay? So I'm not even interested in this bottom point because it's not in the upper half of that unit circle. In the upper half of this unit circle, if I let n equal 0, then that's 0, and I've got pi over 2. And I know pi over 2 is between 0 and pi because I can write pi as 2 pi over 2, and 1 is smaller than 2. 1 pi over 2 is smaller than 2 pi over 2. I have found the solution that they want. Even though there was infinitely many solutions, they only wanted the solutions that were on the top half of this unit circle, which is exactly one solution, and that's pi over 2 radians. All right, so what about this? If they ask me to solve this equation, find the values of x such that the sine of x is equal to -1, there are infinitely many angles that I can replace x with to satisfy this equation. All right, on this unit circle, I can find two of those solutions, or excuse me, just one of those solutions by looking for a point that has a y-coordinate of -1, and I find it down here. And that's the only point on this unit circle that has a y-coordinate of -1. So if I were just looking between 0 and 2 pi, my solution would be 3 pi over 2. I know that the sine of 3 pi over 2 is -1. And I also know if I have any coterminal angle to 3 pi over 2, the sine will also be -1. So I'm going to add complete revolutions or subtract complete revolutions. But I'm going to write 2 pi as 4 pi divided by 2, and I'm going to let n represent any integer. 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. All right, they did not want infinitely many solutions. They want me to reduce this infinitely many. They only want me to find solutions that are between -pi over 2 and +pi over 2. That's on the right half of this unit circle. Okay. All right, so if I let n equal 0, 3 pi over 2 is bigger than 1 pi over 2. It's not in the range they were wanting. So n equals 0 isn't going to give me one of the points that's between here, but n equals -1 will. If I replace n with -1, and now I do this arithmetic, then I get -4 plus -4 pi plus a +3 pi. I get a -pi over 2. And -pi over 2, wait a minute, this says strictly less than. So between -pi over 2 and pi over 2, if I include the endpoints, I can only find one solution. They want me to exclude those endpoints, so this has no solution. I can't find a value of x that will satisfy this equation where they're wanting me to look. They're wanting me to have hollow points here. They don't want me to include those endpoints. They want to look just strictly on the right half here, not on the y-axis. Well, there is no angle, and therefore no coterminal angle that will satisfy that equation. So this number 6 has no solution. Or some people wrote undefined, and that's fine. Now, let's take a look. There's more than one value for x for each problem described. Find all possible values on the interval. So first, before I look at their interval, I'm just going to find the general solution. I'm going to find the solutions over the entire set of real numbers, and then I'll look in the interval they want and see which of my solutions fall in that interval. All right, so when they give me that the sine of some angle is equal to negative radical 2 over 2, because this is negative, and because we're sine, I'm looking for the y-coordinate, I know that that angle will either be in quadrant 3 or 4 because it'll be below the x-axis. And if I look for a y-coordinate that's negative radical 2 over 2, I find two of them, one at 5 pi over 4 and one at 7 pi over 4. So I know that if I replace x with 5 pi over 4, that's a solution to this equation. I also know that I can find infinitely many solutions to this equation by finding coterminal angles. And that means adding or subtracting multiples of 2 pi. And I can rewrite 2 pi to make it easy for me to add or subtract to get a common denominator. So there's one of the solutions here. This equation describes infinitely many solutions to this equation. So I can come over and do the same idea with 7 pi over 4. Any angle that's coterminal to it, I can write infinitely many by letting n be any integer. That's not what they wanted, however. They wanted me to look between negative 2 pi and positive 2 pi. All right? So I know that if I let n equal 0 in both of these equations, what would I have? If I let n be 0 in this top equation, I just have 5 pi over 4. Because when you multiply by 0, you get 0 and you're adding nothing. You're adding 0. And down here, the same reason, 7 pi over 4. Those are two solutions that are in this range. Well, what if I let n be negative 1? If I let n be negative 1, then I've got positive 5 plus a negative 8, which is a negative 3 pi over 4. And here, if I let this be a negative 1, I'll have negative 8, and I'll have negative pi over 4. Since all these denominators are 4, let's come up to where they're wanting me to restrict my solutions. And let's look at negative 2 pi as negative 8 pi divided by 4, because that's negative 2 pi. And let's look at positive 2 pi as positive 8 pi divided by 4. So if I look at negative 8 and positive 8, look here, all of these numbers are between negative 8 and positive 8. Now let's look and see could there be any more? What if we let n be 1? Will we be bigger than 8 pi? Well, yeah, because look, 5 plus 8 is 13 pi over 4. That's a solution to the equation, but it's not in this interval. So therefore you throw it out. What about the other one? 7 plus 8, well, that's even bigger. That's 15 pi over 4. So although those would satisfy the equation, they don't satisfy the constraint. Those are not in my solution set. What if I, in negative 1, what if I went all the way down and let n equal negative 2? Well, 8 times negative 2 is negative 16. Negative 16 plus 5, negative 11. But negative 11 is smaller than negative 8. Negative 8 pi over 4 is bigger than negative 11 pi. This number is too small. It's not my solution. What if I plug in negative 2 here? I'll have negative 16. There I'll have a negative 9. And negative 9 is smaller than negative 8. So I throw it out. So I only find 4 solutions, 4 values of x, of the infinitely many x's that satisfy this equation. Only 4 of them are between negative 2 pi and positive 2 pi. So, infinitely many x's solve this equation. I'm looking on the unit circle for x coordinates that are negative radical 2 over 2. X is negative in quadrants 2 and 3. The points of interest are here and here, at 3 pi over 4 and at 5 pi over 4. So I can write infinitely many solutions to this. I can take 3 pi over 4, and I can rewrite 2 pi as 8 pi divided by 4, and I can do the same thing with 5 pi over 4. That's infinitely many solutions to this equation. But they didn't want infinitely many. They only wanted me to find values of x that were between 0 and 3 pi. All right, so let's see if we can do that. If we let n be a negative value, then these are like negative 1. Negative 8 plus 3 is a negative number, and that's smaller than 0. Negative 8 plus 5 is negative, and that's smaller than 0. So I know that the n is not going to be negative. I'm not going to find, I will find solutions to this equation, but by letting n be negative, they're going to be smaller than 0. So let's start with n equals 1. If n is equal to 1, then I claim that, oh, excuse me, let's start with 0. That'd be smarter, wouldn't it? If n is 0, I'm on that first rotation, and I've got 3 pi over 4, because if this is 0, you're adding 2 pi times 0. And I've got 5 pi over 4. Now, it's hard for me to compare a denominator of 4 against a denominator of 1. So I'm going to multiply this by 4 over 4, and I'm going to look at 3 pi as 12 pi divided by 4. And I can see that 3 is smaller than 12, and so is 5. So the 3 pi over 4 is bigger than 0 and smaller than the 12 pi over 4, smaller than 3 pi. What if we let n be 1? Well, that'll get us 2 more solutions. 3 plus 8 is 11. That's 11 pi over 4. And 11 pi over 4 is smaller than 12 pi over 4, so that's one of the solutions they're looking for. What if n equals 1 here? We've got 5 plus 8, which is 13, and 13 is bigger. It is a solution of the equation, but it's bigger than the 12 pi, so they don't want that. All right. So the only solutions of the infinitely many that satisfy this equation are these, the three that are 3 solutions that are between 0 and 3 pi. So when I looked in the first revolution, I found these 2 points. But then when I started to make my second revolution, I could only go halfway. I could only go to there because that's 3 pi. 1 revolution to here is 2 pi, and then plus pi more, I'm at 3 pi. So I included this guy, which was 11 pi over 4, but I can't include the 13 over 4 because I'd have to extend beyond 3 pi. So these are the only 3 solutions. There's infinitely many solutions to the equation, but there's only 3 in the interval that they wanted me to look for. All right, so what about this? Again, I'm doing the same approach. Since it's a sine, I'm interested in the y-coordinate. The y-coordinate here is positive, so I'm interested in looking in quadrants 1 and 2 for a y-coordinate that's radical 3 over 2. I find one of them right here, and I find the other one right there. So I can write, there's infinitely many solutions to this equation. I can describe those infinitely many. I can't list them all, but I can describe these infinitely many solutions. If we start here at this point with pi over 3, I'll have pi over 3 in any angle that's coterminal, and we'll add 6 divided by 3 is 2. We'll add integer multiples of that, which includes negative numbers, which means going in the clockwise direction. Clockwise is negative, counterclockwise is positive for angle measures. Now, in this other point here, I have 2 pi over 3, and the same idea, coterminal angles to that. We'll have a sine of this angle having the ratio radical 3 over 2. They didn't want infinitely many solutions. They wanted me to only provide solutions that were between 0 and 2 pi. So if n were equal to negative 1, I would have negative solutions, and they'd be smaller than 0. If n equals 0, I'd have pi over 3 and 2 pi over 3, which is definitely between there. If we rewrite 2 pi as 6 pi over 3, we can see that 1 is bigger than 0 and smaller than 6, and 2 bigger than 0 and smaller than 6. All right. So what if I let n equal 1? What if I added 6 to that? Well, 6 plus 1 is 7. That's too big. 6 plus 2 is 8. That's too big. So the only solutions that they want, instead of these infinitely many, are just these 2 solutions, pi over 3 and 2 pi over 3. Those are the only two solutions between 0 and 2 pi that satisfy this equation. Cosine of some angle is equal to 1. I'm going to look at the unit circle and see if I can find an x-coordinate of 1. And I find it right here. Now, this equation has infinitely many solutions. I can describe those solutions by having, that's information about my truck. 0 plus any coterminal angle 2 pi n. Okay, they did not want infinitely many solutions. They only wanted solutions that were between negative 4 pi and positive 4 pi. So here's where the true advantage is in rewriting this as n, because if we replace different values of n, we can get these different solutions, and we can see if it's between negative 4 pi and positive 4 pi. If I let n be negative 3, then I've got negative 6 pi, and that's too small. Okay? If I let n be negative 2, I've got negative 4 pi, and they want me to include that as an endpoint. So this is a solution. What about this negative 4 pi is? What about if I let n equal negative 1? Well, then I've got negative 2 pi. That's a solution. If n is equal to 0, I have an angle of 0 radians. That's between negative 4 pi and positive 4 pi. If I let it be 1, I'll be 2 pi. If I let it be 2, I'll be 4 pi. But if I let it be 3, I'll be too big. That'll be 6 pi. So there were infinitely many solutions to this equation. But of those infinitely many solutions, the only ones that are between negative 4 pi and positive 4 pi are these right here, these 5 solutions right here. All right, I'm back. I was reading the email about my truck. All right, so there are infinitely many solutions to this equation. If the tangent of some angle is equal to 1, I'm not looking at an x-coordinate or a y-coordinate for tangent. I'm looking at y divided by x. If y divided by x is equal to 1, I'm looking for an x and a y coordinate that are equal to each other. Like here at radical 2 over 2 and radical, the x and y are the same. So when you divide them, you get 1. And down here, a negative divided by negative is positive. So those are the 2 points of interest when I'm going to write my solution. Now, tangent's a little bit different because its period is just pi. So when I have x equals pi over 4, I don't have to go around a complete revolution to land at another, at the next solution to this. I can just go to its period. I can just go pi. So I can add pi to this, and I'll write pi as 4 pi over 4. So if n equals 0, I've covered this one. If n is equal to 1, look at this. 1 plus 4, 1 pi plus 4 pi is 5 pi. So this one equation contains these 2 solutions and all the angles that are coterminal to those. So here's infinitely many solutions to this equation. They didn't want infinitely many. They wanted me to look for, they wanted me to work in degrees. So let's write pi over 4 as 45 degrees. And let's write pi radians as 180 degrees. Okay? So if I make this, if I substitute in different values of n and try to find angles that are bigger than, strictly bigger than negative 180 and strictly smaller than 360, well, let's try negative 2. If I plug in a negative 2, then that's negative 360, and negative 360 plus 45 should be a negative 315. Well, that's way too small. I want to be above negative 180, so I throw that out. What about negative 1? If I take away 45 from 180, I'll be at negative 135. Hey, that's in there, right? 0. If that's 0, I've got 45. If 45, that's in there. shrink this up so I can write this all in the same table. All right. So what if n is equal to 1? Then I've got 45 plus 180, which is what? Is that 225? Yeah. All right. What if it's equal to 2? Then this is 360 plus 45. Hey, I'm at 405. I know that's too big. So I know I have to exclude the negative 315 degrees. It is true that the tangent of negative 315 degrees is equal to positive 1. It's just that negative 315 degrees is not in the constraint. It's smaller than negative 180. 405, the tangent of 405 degrees is 1, but 405 is bigger than 360. So the only solutions to this equation that are between these two values are these three, or at least those are the only three that I found. All right, so let's look at the next one here. So it's the same idea. I'm looking for an x-coordinate of 1/2. Positive x's lie here in quadrant 1 or quadrant 4. So with an x-coordinate of 1/2, I'm interested in this point at pi over 3 or at this point at 5 pi over 3. There's infinitely many solutions to this equation. I can write pi over 3 plus any angle that's coterminal to pi over 3 will have that same cosine ratio. I can work with 5 pi over 3 and its coterminal angles. But it didn't want all of the angles. It only wanted angles that were, well, it wants me to work in degrees. I hate degrees. I like radians are so much easier to work with. All right, so pi over 3 is 60 degrees. And 2 pi is 360. And over here, 5 pi over 3 is 300 degrees. And if we add integer multiples, 360. All right, so let's get rid of our radian measure, as much as I hate to do it. And let's work in degrees. So the negative 180 is if you went clockwise, if you went down. So it's going to pick up this point and this point down here. So if I let n be negative 1, if I focus my attention on this equation, and if I replace n with negative 1, then I get positive 300 minus 360 is a negative 60 degrees. So then if I come in and say, well, I'm going to let n be 0 for each of these equations, then I pick up a positive 60 degrees and a positive 300. And that's between bigger than negative 180 and smaller than 360. If I replace n with 1, I'm too big. I'm at 420, I'm at 660. These are the only three. Because remember, when I did it with negative 1, this guy to go around here and end up there, that's going to be too small of an angle. This is negative 300, and negative 300 is smaller than negative 180. It's not in that range. So it's only these three angle measures. Of the infinitely many angles that satisfy this equation, there are only three angles that are between negative 180 and positive 360 that satisfy that equation. All right, so here I've kind of cheated a little bit and used a graphing program because I can't freehand it well enough for you to really look at and maybe get all the information that you'd like. So here in this first table, we just picked, I just picked some major values. Let's see, I can't see here. Boy, did I when x is pi, it's 0. Yeah, so there, there. When x is negative pi, there, there. At negative 3 pi over 2, here, I'm up here, and that's at 1. And at negative 2 pi, I'm back down here to 0. At negative 5 pi over 2, I'm down here at negative 1. And you can see at 3 pi over 2, I'm down here at negative 1. At 2 pi, I'm back on that center line. And at 5 pi over 2, I'm up to 1. So there's just some points off of my sine curve, and you're familiar with those points. The idea of an inverse is to switch the domain and range. So you can see that we just took this table and switched the x and y values. If we plot these points, and we don't connect the points in a straight line fashion, we kind of, again, we're kind of cheating a little bit. We know it's got a curve to it. We know that if we went into more detail and plotted more points, that it would have this curve feature to it. Since we know that, we kind of fudge a little bit and make it look curved. If you plot all these points, what you'll notice is this relation, okay, it's a set of ordered pairs, but it fails the vertical line test. See, it says sketch the graph of the inverse. We did that in green by using this table here in B, but is it an inverse? No, because it fails the vertical line test. I can write a vertical line that intersects this graph more than once. It intersects that graph infinitely many times. So there's no way that that relation's a function. Cosine is the same idea. We took some points off of the cosine curve. Let's see, pi negative 1 is there, negative pi, negative 1. See how it's symmetric with cosine's even. So the cosine of pi is the same as the cosine of negative pi. And the cosine of negative 3 pi over 2 is the same as the cosine of positive 3 pi over 2. That's because of this even property, that it's symmetric with respect to the y-axis. So those are all points that we've worked with that you're pretty common with. We could have gotten more detail, but it's not necessary because we're just making a sketch of it. If they want a super detailed graph, we live in a world of technology, and we can use the graphing calculator like I've done here to do that. The idea of an inverse is to switch x and y. So then if we plot all of these points, if we connect the dots, if you're not thinking in terms of a cosine, you'll probably connect the dots in a straight line fashion, but we know that there's a curve to it. So as we are plotting those points, like if we look at 0, negative 3 pi over 2, here's 0, here's negative 3 pi over 2. You know, negative 1, negative pi. Here's negative 1, here's negative pi. I didn't just draw a straight line in here. The computer knew to kind of curve that in. It knew, because it actually, looked at more points than just are in our table when it did it. That's why its accuracy is a lot better than what I could do just by freehand. So anyway, just by the same reason the previous problem, this graph fails the vertical line test, so it's not a function. The inverse of this cosine is a relation, but that relation is not a function because the original cosine was not a one-to-one function. And that's true with the original sine function. It was not a one-to-one function. So I knew at the very start of this problem, since I'd had a function that was not one-to-one, that its inverse was going to be an inverse relation and not an inverse function. Now, I did not have you actually sketch out the tangent, but you could. I just thought that people might find it a little bit difficult because if we start with the basic tangent curve, we've got all these vertical asymptotes. It's undefined at odd multiples of pi over 2. So my graph never touches. The red lines get closer and closer and closer, but they never touch these vertical asymptotes. Okay, so here's some that we just went it rather than dealing with the tangent of pi over 6 is radical 3 over 3, and the tangent of pi over 3 is radical 3. We just looked at it, tangent of 0, 0, tangent of pi over 4 is 1, and the tangent of 3 pi over 4 is negative 1, The tangent at 5 pi over 4 is positive 1, and at 7 pi over 4, you're in the fourth quadrant. The tangent at 7 pi over 4 is negative 1. So we just went back and forth between 0 and positive 1 and 0 and negative 1, and we just plotted pi over 4, 1 right there. Negative pi over 4. See that faint blue line right there is negative 1, and this faint blue line right there is x equals negative 1, x equals positive 1, y equals positive 1, y equals negative 1. So then that's in that first, that's these 3 points. Then if you look at these 3 points, they're over here, not there, right here, and right here. And if you look at these 3, they're over here, this, and this, and this. So we kind of fudged a little bit, knowing that a graph gets closer and closer to its vertical asymptote, and that you're already going up. And here that you're getting closer and closer to vertical asymptote, and you're already going down. And even though these 3 points do fall on a straight line, we knew from experience that these have a curve to it. So that's how we curved in. If you're doing it by hand, you'd have a little bit of curve at each of those places. And then because the vertical asymptote, it's going up, so it's just going to get closer and closer to this line, x equals negative pi over 2. And here it's going up and getting closer and closer to positive pi over 2. And here at negative 3 pi over 2, the graph is getting closer and closer without touching. So that's how you're able to sketch the tangent curve just by hand. All right, now if you switch x and y, what happens is this middle portion that's going through the origin here, when you switch x and y, it's a reflection across the line y equals x. So when we reflect that, what I've highlighted in yellow, you get right here what I've highlighted it in yellow on that green. So if I look at this guy, and its reflection is over here, and if I look at what this one over here, it's crossing, this is in my way. It's this one right here. So take some time to look at that, but don't spend too much time on that. Hey, I hope this helps, and I'll talk to you later.